as you can see, you will all see my screen, right?
Yes.
Okay, cool. Xomnia is an AI consultancy organization. We are located in Amsterdam, founded in 2013 and growing very rapidly. When I joined in 2016, we were with about 30 people, and today we form a big family of 80 people and still counting. Our main activities contains the projects that you see here, X-Force projects where we work with a team of Xomnians on a specific use case for the client. And we also do consultancy where we blend in with an existing team at the client. We have the MLE traineeship, which is a program for people with already some working experience, 1 to 2 years, in either data science or data engineering, and who want to develop in a more hybrid role as a machine learning engineer. And we have the Xomnia Academy, in which we offer training to our clients on a broad range of topics in the data science and engineering field. As you can see, our clients come from a variety of sectors, amongst which logistics, retail, the financial industry, governmental institutions, and the medical sector. Xomnia also has a venture, shipping technology, where we work on autonomous sailing and for inland shipping. And last but not least, we strive for responsible AI, and therefore we host webinars to share knowledge on this important topic. And we have partnerships with the Ocean Cleanup and UMC, which is a hospital in Amsterdam, to whom we make our knowledge available. So this is Xomnia in a nutshell, but if you want to know more about our activities, you can always have a look at our website, where we share in more detail. And then it's time to introduce today's speaker to you, Eran. I got to know Eran as an energetic and social and above all passionate data scientist with an impressive track record, which he will tell you more about in a moment. The first time I met Eran, we discussed the possibilities of setting up a training program for his data scientist team within APG together with Xomnia. And the second time I ran into Eran was when I myself wanted to learn more about a specific loss function used for reduced regression called the Huberloss. And I found a good blog via Google, and I wanted to save the link for later use. And that was when I found out that Eran had just shared his knowledge with me on eranraviv.com. So the amount of blogs on his website, combined with the motivation to create a full training program for his team, shows the importance that Eran puts to learning and sharing knowledge. And I'm very happy that tonight he wants to share with us his experience with using speech data, the type of data that is not very common within everyday data science projects. And the combination of machine learning and emotion recognition is something that I personally, with a background in statistics and psychology, find very interesting. And I think that the same holds for the rest of the audience. And therefore, I am happy to give the floor to you, Eran. But first, let's unmute and give you a warm welcome. The floor is yours.
Thanks a lot, Lizanne, for the wonderful introduction, setting the bar and the expectations very high. Thank you. Thanks a lot. First of all, I start by extending my sincere thank you for having me. Maybe a few words directly on the actual session. You know, everything now is online, super boring, to be honest. It's very difficult, very different than in real life, and being in a room with everyone and getting the feel of whether people understand, whether they find it funny. What I would like to do, given the fact that we have, I don't know, 30 participants, if possible, just feel free to unmute yourself and then fire away the questions. Would be nice, I think, for other to hear what you want to ask, and it breaks a little bit the monotonic rhythm of staring at the screen. You know, today is a fun lecture. I start by, of course, introducing myself, introducing APG, but the actual experiment, which I will discuss, is sitting in the stitch between audio analytics and deep learning. And so I will also ask you, I'm just wondering, I don't know if here, yeah, you can raise some sort of a digital hand. And I would like to ask, how many of you consider yourself to be familiar to a good extent with deep learning? That's the question. So we have 30 people. Would be nice if you raise your hand if you think, okay, I know deep learning quite well. So you can raise your hand right now. I'm just counting silently. It's about call it 17% of the people. So not a lot, about 20%. There will be some deep learning quizzes for the audience to check your familiarity. What I want to do now is to see if I can share my screen. You should now be able to see audio analytics. I think, yeah.
Yes, we see it.
Yeah, audio analytics. Maybe I start by introducing myself. As Lizan, she mentioned, what should I say? Let's do personal. Married, 2 kids, grew up next to Tel Aviv, came here for school. My younger brother studied in Rotterdam. I did applied statistics in Tel Aviv as a master, and then I came here for a quantitative finance master, and then I got an offer to pursue a PhD. I did a PhD. I have some publications, and then I was sponsored for the job market. Did not go for the academic career because a headhunter asked, do you want to work for APG? They have a nice team. And then the timeline was very quick. I joined about 8.5 years, did a few different roles: senior quantitative strategy, a senior researcher in a front office. And in the last, say, 3.5 years, I've been working as an expert, or actually as a senior researcher. I recently got promoted to an expert at what used to be called innovation, and now it's called digitalization team. And a little bit, maybe very quickly, I will start by explaining the mandatory introduction for APG. This is where I work. A little bit about audio analytics, some technical details on the actual use case. And there we discussed a little bit deep learning. It's not super technical presentation, but a fun one. On APG in general, global organization. APG is a pension fund, and APG-Asset Management, that's the pension fund money manager. So a pension fund, this is like the whole mechanism that cares for the employees. The biggest client by far is ABP, so all the government-related sector. And you can see here teachers, universities, medicine, police, firefighters, and whatnot. And then we have some other clients. So 700 people, different organizations, and the goal is to every euro that is being saved, we need to deliver when time comes, i.e. when the people, they retire, we need to deliver what is owed. And what is owed is a function of what is it that we are able to, to deliver. Now I'm going to share the idea behind this experiment. So this experiment has something to do with, so the way we work at APG, we have idea. The idea, they come from the business side of things, so from portfolio managers, the business edge of the knife, so to speak. So these are the guys that actually doing the heavy lifting. And the idea is simple. So we are now end of April. I think we are just winding down the earnings season. And what is earnings season? Come beginning of, say, April, and then we start to have press releases or earnings calls. An earnings call, that's one of the main sources of information for a portfolio manager to track a name which is in their portfolio. A name meaning Microsoft or Apple or Netflix or Tesla or what have you. And because we are talking about the first quarter, which ended at end of March, but we are already quite deep into the second quarter. The rationale is the people who are given the presentation and answering questions, they already know quite a bit about how current quarter, which is going to have a press conference or a press release just in a couple of months, 3 or 4 months, but they already have a good feel how is the current quarter already, how are things going. And therefore, they might have more information than their actual transcript, which is written for them when they speak. So the idea is perhaps we can add to the collection of signals that our money managers have in their mind from experience, from looking at the data. Perhaps there is more to the tone of voice. So I think you can tell, at least from this story, I'm quite comfortable with the story. For whatever reason, you can, I think, feel it. And if I would be mumbling or uncomfortable, you would also feel that. So the question is, hypothesis is that we can perhaps figure out, not from the actual content, from the how things are being said. So this means working with audio data. That's difficult. I would like you to grab your iPhones or smartphones. You have an app there. If you did not erase it, the app is called Voice Recorders. So that's the app. I'm looking for. I don't want to. Voice memos or so. I don't want to share my but go there, and then press record, but don't say anything. Just blow into the device like this, and have a look at the. You see? So what is audio? So I'm now speaking to the microphone. It does not record the actual sound. It records. It's a very sensitive device that records air pressure. So that's the data. I had to figure this out, because you get an MP3, then you start thinking, okay, what am I going to do with the MP3 file? What kind of data is it? So then I thought, okay, let's have a look. And so this is air pressure. It is a continuous time signal over time. This is how it looks like. That's a typical file. I think you have seen this file in the past on your computer. This is 1 hour and 2 minutes, 51 seconds of conversation. So the way it went is simply a press conference, just like this presentation is recorded. So that's going to be data. And by the way, this is an overarching vision to quantify or to try and disentangle more, or to quantify soft data, because everything is data. Everything that you use to make decision is data. And data is not only stored in Excel or rectangular tables. Bit rate is how it is actually recorded. Think about it as pixels, resolution, and so. And what we need to do, we need to bucket this, because we need to make it what's the word here? We need to bin it, to digitize. We need to digitize it, because the computer cannot work with a continuous signal. So what we do, you have a continuous time, and then you measure it in some point in time. Of course, if I measure, 1 point out of 1 hour, it will not give me much. But there is a theorem that says this is okay to do if you sample often enough, you can recover the actual signal. And this is how it looks like. This is the sample rate. This is every second you have 11,000 numbers, which is not very, very high resolution. And when I got the data and I thought, okay, let's have a look how it looks like. Boom. Because it's 1 hour of data, 11,000 numbers per second. Overall, I try to plot, I don't know, 4 million points on my desktop. And of course, don't try it. And then I did want to see exactly how the data looks like, because to get a feel. And this is, if you snapshot every 10,000, actually the reverse. If you request, I would like to see 10,000 numbers only out of those 4 millions. So you have 4 million numbers. This is the data. So this is 1 hour of conversation, very ugly. Bear in mind, we are now discussing how audio data looks like, but I want to remind you what is it that we aim to do eventually is to see if we can label based on this kind of data, these kind of images, whether the speaker, say, is happy or is very sad or is very agitated. That's where we are going with this. So this is time series audio data. And this is a very, we are now going for a signal analysis, because we have few ways to represent the data. One is what is now I described, which is time over time, just air variation pressure over time. And what I want to do is I want to move forward from this time domain, that's how it's called, time domain, to what they call frequency domain. And I will explain what it is. But before I explain, I want to show you, if you zoom in on the data, because this is basically domain-specific audio analytics when people, they talk. So the way it goes with their air variation is sine wave, or a wave, not a sine wave, but just a wave. And this is a really a randomly chosen 0.007 seconds out of the, so you can see it, if you smooth it out, it does look like this kind of wave. And there is a few features. You just saw this very ugly, like a pacemaker image, but we can extract all kind of call it engineered feature from this. What kind of features we can extract? One feature, we can have a look at the auto-regression of that series and think about it as a feature. If you Google, maybe not now, but if you Google Rob Hindman, they actually engineer the R package where you give them a data series and they give you back like 11 different features just from the time series. These features are like auto-regression, first order, second order. These are numbers that are a derivative of the original series. Now, frequency is also such number. And frequency is if you chop a period, so you can count the oscillation inside that period. Low oscillation, that means a very low frequency. High oscillation, that's tick, 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 the high frequency. And this has something to do with how sound transfer over the, it's called, I think sometimes it's referred to as a pitch, high pitch, low pitch. what I want to do is I want you to listen how it actually looks like. What I'm not sure about is if you can hear this. So let's have a look. Can you hear this? Yeah. So I'm going to start very low. By the way, you know this. If you go and buy a speaker, there is a huge variation. There is a huge community of audiophiles, and you can buy speakers and headphones. Google. Let me give you an interesting reference. Yeah, you can Google Focal Utopia. That's a headphone. Focal Utopia. See if you can, if you feel like buying something like that. And what the hell is so expensive? You know, it's very expensive headphones. Focal Utopia. What is so expensive? And then one of the things that are expensive is how accurately these kind of waves are actually captured, and what is the frequency that is able to be transferred. So for example, very low frequency, you will see that I'm not changing the volume, but you will see that it's very hard to listen to. So this is the actual volume, you can hear it. But if I move it to a very low frequency, you can barely hear it. Even though it's the same volume, same everything. And it's slowly you will hear the bass. And I think human ear in general, below 20 hertz, we don't hear it. But this is what makes speakers, or part of what makes speakers and headphones so expensive, is how accurately they are able to replicate this. Let's continue here. This is kind of like higher and higher. You can see the oscillation. This is a high frequency. That's, you can also see why they call it frequency, right? Because of the oscillation. And this is more for dogs. This is the dog whistle, which we cannot hear, but the dogs, they can hear it. Yeah. So that's this. And this is how it looks in the time domain and in the frequency domain. The colors here has nothing to do with the amplitude. So for example, you have high colors here as well, but here it's not a high amplitude. It's just high oscillation, and you can hear it. So that's a dog barking. This is how it looks like. And these are all kind of features that you can derive. You know, autoregression I mentioned. You know, you have a lot of those. Yeah, zero crossing, amplitude, of course, the level, power is, you can simply square the series. These are features, and those features, mind you, they can simply go in some regression. So once you have those features, you can make an actual regression. And my point is how to move from MP3 data, audio data, to something that you can actually work with. So you start with all those numbers, you construct features, and then you can create the model. This is some features that we considered. It's a lot of signal processing, MFCC, that's some sort of really domain-specific feature engineered. And we are now moving to computer vision. I repeat the task. The task is to see if we can figure out what's the emotion of a CFO when he speaks. This was a joint collaboration with the PhD students and researchers as well, people who know a lot about convolutional neural network and so. And they made a very interesting point. So that was the idea that we settled on. The point was, you know, this is just an image, and we know already quite a lot about images. We know much more about images than we know about audio. Images is just pixels. I don't know how much you know about images, but this is just a pixel, and this pixel has three values, which are red, green, and blue variables. And you can think about it as explanatory variables. So if I stack this image, let's assume we have, say, 4 pixels. 1, 2, 3, 4. Each such pixel has 3 values, and I can stack them, and this is my explanatory variable. Of course, we have many pixels, but it doesn't matter. This is how it looks like when I read some logo of ours. You read it. You can do that in R or in Python. You can read it. The dimension, this is the dimension of the image. These are the number of rows. These are the number of columns. Think about it as pixels. And why 4 and not 3? Because we have also a value for if it's transparent or not. But in general, this is red, green, and blue numbers, just numbers. And you can scale them. You can do whatever you want. You can see that overall we have here like 1,482,500 explanatory variables, which are the pixels. These can be used as explanatory variables. And now, because we know so much about vision, computer vision, enter deep learning. And what I want to ask you, what is so deep about deep learning? What is actually being learned? So for those people who raise their hands, I want to ask, that's a question for you. If you can unmute yourself, and I want to ask the question, what is actually being learned when we apply deep learning? What is it that we are learning exactly?
Are we learning the patterns? I think we are learning the patterns because when we do the in a neural network, we usually when we work with the image, we try to split the image in various parts, and we are trying to extract information from that. So I think we are learning patterns.
Yes, I agree with you. That's very nice, Renan.
Yep, Renan.
Yes, absolutely. So it's actually quite rare that I get the right reply, but we are learning how to transform the excess such that we are good to introduce those excess, those original variable inside a model. How do I mean such that we are good to do it? I mean, computer models, they are good in thinking linearly. So if you can find a nice combination of the original excess such that before you step out, it looks kind of linearly separable, then you're good. You will get nice predictions. But if you are not, so for example, if you apply on the left-hand side, you have some sort of a picture, an image simulated, and if you try to apply, say, logistic regression in order to classify those points, then you will struggle. The logistic regression is gonna provide you poor results because this space is not separable linearly. What I did here on the right-hand side, you can transform it. I coded polar coordinates, but if you introduce those polar coordinates to a logistic regression, you will get nice results. And what deep learning is doing, as Renan mentioned, you don't need to code what is the transformation. The deep learning is going to search for it. That's what the learning in deep learning, the whole field goes under representation learning. And why representation? Because we want to re-represent the original variables. And we did not want to invent any wheel. So bear in mind, where is it that we are moving? We are moving from the audio towards image classification towards labeling. So we are now on the image part. So we have an image, which is basically the frequency, as I explained. And now what we want to do, we want to apply a deep learning model. and to see if we can label correctly. I will, in a second, we did not yet discuss, how did we even label the data? I will discuss this in a second, but we are now only talking about the model. So we chose a well-established visual recognition or computer vision model, which is called VGG. You can download the weights from online. So the way it goes, you basically download the weights, you adjust whatever needs to adjust, and then you can basically apply this model, because a model, when we say a model, we mean nothing more than these weights. And this is the architecture of the actual model. We don't teach here a convolutional neural network. There is all this business here. So these are the pixels. And think about it, up until this point in time, the computer, when I say this point in time, I mean the light blue. Up until the light blue boxes, we are simply searching for a nice transformation of the original pixel, such that before we step out, we have a good feel for is this guy amused or happy or sad or annoyed, or label it. This is how the model this is how the model looks like. Just in Keras, standard, 700,000 parameters, very nice. We need data in order to train the model. Very difficult. As opposed to what you can find in, say, in the literature. We tried putting those MP file on Amazon, for example, and let people annotate sentence by sentence. Is this guy happy? Is this girl happy? Annoyed, confident, these kind of things. And we actually paid for this in Amazon. It has this Turk machine or something like that. I was not in charge on data collection, but very dirty what comes back. So our experience, people, they want to get paid and they don't really mind what is it that they are tagging. So they are not very serious about this. And then the rationale was, maybe we let the portfolio manager listen to it and build our data set like that. And then this was difficult for them. And then we thought, well, maybe psychology students, on the grounds that they are more sensitive and they are more attentive and they know a lot about how people they communicate. And then eventually we reverted back to portfolio managers. What I want to let you do now, I'm going to share a link, and we make some sort of an experiment here. And the experiment is whether you yourself, you can, I'm gonna let you listen to a couple of sentences, and then you will, you can click on that survey, and then you can tag basically what is it that you think the speaker is. I'm gonna make sure this is. I'm going to do that again. And we are pricing Fiverr very aggressively, quite intentionally, because we want to get people on Fiverr, and we make we are pricing Fiverr very aggressively, quite intentionally, because we want to get people on Fiverr, and we make. So feel free. You can click what is it that you think the speaker is. This is some sort of, I don't remember the name of the company, but I think it's some sort of an infrastructure, internet infrastructure, and Fiverr is something to do with the optical connections or wireless internet infrastructure, I guess. We are pricing Fiverr very aggressively, quite intentionally, because we want to get people on Fiverr, and we make. One more time, and then I share the results.
We are pricing fiber very aggressively, quite intentionally, because you know, we want to get people on fiber. We make
okay. Now I share with you the result of this experiment. Let me see what kind of can you see this window?
Yes.
Yes, very good. So that was our experiment. I don't. I'm looking for how many people actually replied. I wonder. I don't know. But yeah, I think a lot of people replied. This is typical. What is it that you see is that perhaps the speaker is stressed. But a lot of people said neutral or frustrated. Some people, they said optimistic and content. You can see that this is optimistic, excited, and content is the reverse from a frustrated and stressed. And spoiler alert, that's the problem with this experiment. When I say problem, I mean it's very difficult to say why is it that you think something about how someone have said, or you know, it's very intuitive and not very data driven. What you think you know and why you feel what you feel is not you cannot basically explain to anyone why is it that you think so. And do you see what Lizan, what do you see now? You see the process of collecting data still?
No, still try and annotate.
Ah, that's not good. You can see my share. So I want to move to the actual result. So this is what I just told you. It looks to me as if, yeah, you know what you know, but it's very hard to say why. You know, I mean, sometimes you just feel something, and portfolio managers and people in general, they are very good at this, and extracting these kind of nuances from tone of voice is very difficult. And what we did, I'm now sharing with you a little bit the results. They were not impressive. That's like the bottom line. So we did a lot of work on this. It's very difficult. There are two kinds of mistakes. One mistake is, you know, you annotated that, or the model says this guy is optimistic, but he's not. And then the reverse is also a mistake, saying that this guy is neutral, but it is optimistic. And very much like in sentiment, the problem is that there is no ground truth here. So for example, we just made this experiment, and I would tag that snippet maybe as stressed, but you can see that a lot of people, they wrote neutral and excited and optimistic, and this can also be true. So the ground truth is invisible here. And then finally, we have tried, should I get into details here? Maybe yes. I wanted to forget a little bit about accuracy and see whether we can actually use it. And when is it that we can use it is, okay, not accurate. But maybe we, every time, so it's very inaccurate, but maybe every time CFO or CEO is negative about something, the model actually captures this. So highly inaccurate in general, but maybe we can direct the portfolio manager to those places where the model, and then maybe it's cheap. What do I mean it's cheap? If we can direct, I don't know, 10-15% of the time, then yeah, the portfolio manager would spend some time. Most of it is useless, but sometimes it's gonna agree, and then basically you call it attention. You know, you direct attention. But this was also not promising. So, for example, if the model had unconditional coverage of 60%, think about it as a coin toss where 60% of the time it's heads, and then the model, sorry, 50-50. A fair toss. Yeah, a fair toss. So if the model says 60% of the time it's heads, I would expect for a good model to capture at least 60% of the time where it's actually heads. And then I would think to myself, okay, the model is not that bad, you know? But, you know, even after accounting for this unconditional coverage, it's it was not promising, you know, to keep using this, because if 60% of the time you say something and 60% of the time you are right, even though it's 50-50, then you don't have any advantage. Yeah, it's a little bit of a blurry explanation. Cut a long story short, results are not promising. That's it from my presentation. So key here is that audio data is quite difficult, and maybe it's interesting for you to know. We have then went into vendor selection. This field is fantastically promising in the sense that I think with a lot of data, you can extract meaning from only tone, but you need a huge amount of data. You need to benchmark this to the speaker, and that's, I believe this is possible. And the second one is it's not yet solved, as opposed to, say, text analytics, which is, you know, I would not go and open our startup in text analytics because there is so much done in that space. So it's more or less solved. I consider this to be solved. We know so much about text analytics, while audio is still up and coming. And it's also for us, I mean, for us as an individual, as opposed to Apple and Google and Amazon. Yeah, that's it. If you have any questions.
Yeah, thanks, Eran. As promised, I will shut down the recording.